Now, a couple months ago, I got bored, so I decided to create this a chess robot that plays chess against a human. Now, the way I built this involves three core components the hardware, the software, and the electrical. In this video, I'll describe how I did each step, and also at the very end, there will be a demo of this project in action. First, I modeled all my parts in SolidWorks. Then, I mated these parts together in subassemblies. I finally mated all these subassemblies together into one big assembly. This is the final look. Next, I converted my SolidWorks part files into STL files and 3D printed them on my A1 printer. I used PETG for strength properties. In terms of the mechanical aspect, I think the biggest issue for me was finding the right tolerances and clearances so that all parts could fit nice and comfortably in their holds. Next is the software aspect. So this is my Minimax algorithm, and it works kind of differently than the typical Minimax algorithm. And that's because of four components. To start, I just want to mention that this Minimax algorithm is working in favor for white, since the chessbot is blank white. The first component is how I evaluate moves. In addition to evaluating material and pieces, I'm also evaluating the score based off the opponent's mobility and the number of squares they can go to. The second component is how I evaluate checkmates. By adding a penalty to one side, I'm able to accurately say that's a checkmate, and the Minimax algorithm is more likely to pick that as the best move. By multiplying by depth plus 1, I'm also able to provide the checkmates in move of 1 to have a higher preference over checkmates in a move of 3. The third component is my alpha and beta pruning. Now, by using alpha and beta pruning, I'm able to be more efficient in my algorithm and get to higher depths within the same amount of time. The fourth component is how I return the best move, which is difference. So by doing this, I don't have to have an additional tracker to find what the best move is according to its score. I do it all in one. My Vision/OpenCV code. There's a couple different functions here, but here are the four main ones. To start, we have the board setup function. Now the board setup function essentially just lets the user enter in the four corners of the board using mouse clicks. Once the user does that, their positions are returned and then used in the board update function. Now the board update function uses these positions to do some transformations like warp perspective, get perspective transformation, and essentially they use these to get a nice clean board displayed. We use this clean board to do a couple different properties. The first is we convert the color into gray, and then we apply a threshold such that we only have black and white pixels. From here, we use the find contours function to find the black pieces, and we find the middle of each black piece, and we return those positions of each middle using the locations variable. And this is sent into the piece in square function. After I get these positions, I divide it by the length of the height of each square. In doing so, I'll get a number anywhere between 0 and 7. I then floor this number to get an integer value. I then compute these two integer values, the x and y, into a file and rank for the chessboard. I then return these square locations into another array. The evaluation board function uses both the current setup and compares it to the previous setup to see which piece was moved. And the piece that was moved is then returned as a string. So this is another important file in my project, and this file hosts all the functions to move my servo motors. Now a lot of the stuff here are pretty basic in the sense of understanding, but I really want to touch upon these two functions right here. And they both use a concept called threading. And threading is just a way to move two motors, or in our case, two servos, at the exact same time. The first function I have here moves both the arm and the wrist motors together at the same time. And I use this to pick up a piece when I want to go straight down, okay? The reason I found the need for this is when I first tried to pick up a piece, I noticed that if I were to move them one at a time, I would often knock over the pieces beside it, or even go straight into the ground. By using this, I'm now able to only focus on that one square where the piece is, and not worry about the squares nearby it. My second instance is to move my arm and forearm motors, or servos, and by doing this, I can get to a position much faster, and also, it completely removes any possibility of hitting the ground or knocking over another piece, because they're moving at the exact same time. Now, I didn't necessarily use this function directly in my project, but it did help me accomplish something that would have taken me way longer. And this file uses something called inverse kinematics. And you can think of inverse kinematics as a process, and it's usually in robotics, to calculate the joint angles to place a robot's end effector, right? An end effector in my case would be the grabbers. And it does this by using the desired output to work backwards and find each joint angle. So it uses a couple different trigonometric functions to accomplish this. So the way it works is I took measurements from the middle of the robot to each square of the board, right? And I took three inputs. I took the x value, the y value, and the z value. And when I mean value, I mean distance from that middle, right? And it's measured in centimeters. And anything to the left of the middle is negative, anything to the right is positive. And this y is distance going forward. And it increases as you increase the rows, right? And this y is the distance from the ground to the top of a piece, right? This is just a rough estimate. 10.5 is it's a nice value because it gives a lot of clearance to work with. Once the calculations are done through the Python file, they're then sent to this JSON file, and this JSON file has all the degree values for each servo motor to move to each piece. I then had to manually tune some of them, but for the most part, it was pretty accurate. I've also attached a piece of paper that has all my calculations of how I did the inverse kinematics on my GitHub, so please take a look there. Now onto the components. To complete this project, I decided to use a Raspberry Pi 4. The reason I decided to use a single board computer over a microcontroller is because I wanted to do everything on one machine. I didn't want to compute some stuff on my laptop and then just use the Arduino as a microcontroller to power my servos. In addition to that, I also use two MG90S servos and three high torque servos, two of 20 kg/cm torque, and then the third one of 35 kg/cm. And that's just because of just how much weight the arms and joints are. And finally, I also use a USB camera to do my OpenCV.